So good morning, everyone. In my chat window. So I think there's a few days left before we need some subjects on presentations and things. I think if I remember right, the deadline's October 1st. Check the syllabus, but just I think you need to have a subject idea. If you, Michael and Lucas, if you guys haven't already discussed, you might want to. I think you might be the only undergraduate students registered for the class. If you haven't met each other in chat, you should, because you probably do well working together. I'm gonna have to send out an email to all the MMB students, because I note that none of them are joining us for the lecture today. So what I want to talk about today is last class we discussed ankymeric effects, or ankymeric assistance. We, in excruciating detail, went over the kinetics of the anomeric effect. So today I want to talk about some considerations on glycosylation. So what drives glycosylation and selectivity, and some cool effects that you can use to manipulate for your own profit and benefit. And then I think we want to talk about one other sort of overarching thing, which is the problem with manose. And then we'll move into a series of different glycosylation strategies. And I think depending on how this goes on Wednesday, we might have a conversation with the group on how to direct the course going forward. Because I was going to generalize it more for more of the MMB students with a lot less chemistry background, much more sort of material science. But if that's not a major component of the course, then we could sort of stay more on a chemistry, or we could switch to a more biochemistry perspective for some of the remaining portions of the course. I'm open to discussion on that. So, but back to some of the stuff I think that we do need to cover. So if we have an example. So start more with still with these anomeric bromides. So these are these Koenigsegg conditions. And then nucleophile. And let's just say it's methanol for now. I'm just going to define their nucleophile as methanol, or we could also call this our glycosyl acceptor, as we discussed. So if you remember back when we were just, remember back to last class, this whole Monday, Wednesday thing is tough because then the next Monday is like 6 days away, and I think all of us can't remember what we were talking about. So, here, I'm just gonna turn on my camera. So I'll probably gesture wildly. Okay, so we have the silver triflate. If you remember, that forms oxalocarbeniums. It strips away the bromine completely. We get an oxalocarbenium. Then we're at the whims of oxalocarbenium chemistry. And again, as we start talking about these other glycosylation techniques, a lot of them are going to make oxalocarbeniums. And it doesn't matter how you get to the oxalocarbenium. Once you're there, you're there. And you get these controls on whether you get alpha or beta based on other effects. So the silver triflate is set, and it's going to give us the oxalocarbenium. So we know that this is going to go through an oxalocarbenium intermediate. Now, we can affect the alpha-beta ratio, as we were talking about last class, through ankymeric assistance. You stick a participating group at C2, some form of ester or amide, so they make a 5-member with that oxygen, and you'll get beta. We do not have a C2 participating group, we have a benzyl group. It can't do anything, so that's not going to favor it. And so the anomeric effect favors alpha under these conditions. And we can expect to get kind of like a 3-to-1 ratio, more or less, of alpha to beta. I'm not writing that number down because it's probably not accurate. And secondly, the actual values don't matter. We're only going to really be thinking about relative values because they're really highly dependent on the precise nature of the nucleophile. So if we know we're going through an oxalocarbenium, what I want to start today by talking about is the effects of these two things, temperature and solvent. We're actually going to start with solvent. There are 3 classes of solvent. Okay, there are 4 classes of solvent. As far as glycosylations goes, there's like millions of different types of solvents, right? There's so many solvents. But 4 classes of solvent as far as glycosylation. So these are specific mechanistic classes. And we'll talk about sort of overarching ideas that we can get from organic chemistry in general. So class 1 are non-participating. These are solvents that don't participate. Participating. So some good examples of that: dichloromethane, hexanes, toluene, chloroform, i.e. no reactive heteroatoms. So no nitrogens, no oxygens, no sulfurs. These ones are the easiest. So they don't participate. They don't really influence the alpha to beta ratio compared to the baseline. They are actually the baseline. Dichloromethane is normally used as the baseline for these to get the baseline alpha beta ratio because it has no influence on the oxalocarbenium. It does not interact with the oxalocarbenium. Now, if I had more space, I would write class 2 right below there. I don't, so I'm going to write class 2 up in the corner, and I'll change color just so we're a little bit clearer. These are the ethereal solvents. So what do I mean by ethereal? I mean solvents with ether linkages, although any kind of participating oxygen does it. So, and even nitrogen, so THF, ether, those are the 2 most common, but dioxane, even things like DMF and DMSO. And so we'll see why these do. These guys favor alpha. Class 3 is acetonitrile. It's off on its own. Favors beta. We're going to talk about why alpha and beta because I always care about why. Class 4 changes page. Class 4 are the reactive solvents. So these are solvents that actually will react with the oxalocarbenium. So they're not really solvents, they are nucleophiles as well. Methanol, water, amines, alcohols. I don't know why you would, but you can do reactions in thiols as well. It'll be a really stinky solvent. Not in my lab. We can avoid it, but you can. And so all of these ones, of course, kinetics similar to baseline. So they are going to generate a ratio similar to the alpha beta baseline. And it's because they are going to react as soon as they come in contact with the oxalocarbenium. And so you tend to get sort of the kinetic profile of these things, what's preferred, which is what you kind of get at baseline. So it's even faster. Because as soon as the solvent comes into contact with the oxalocarbenium, it reacts as no longer an oxalocarbenium. So this class 4 is less interesting. Class 1 isn't really interesting because there's nothing I can say mechanistically. It doesn't change any discussion we've had. We could have had every discussion we've had about alpha beta selectivity so far, about anchimeric effect or anomeric effect using dichloromethane, and the dichloromethane just does not come into the conversation. And if you use dichloromethane, it does not come into the conversation because it doesn't do anything. It just solubilizes shit. Class 2 and class 3 is where I want to spend a bit of time because these do things. So let's think about that. Okay, so let's say you have an oxalocarbenium that's out there minding its own business. And your solvent is ether. Now, I've got nothing wrong with the ether, and it's the, as I said, I think we drew galactose on the last page, so I'm going to draw it here. So again, that's my short form for galactose. I've drawn the C4 axial, and then I've drawn a line from the middle with just a benzyl. So I'm saying this is perbenzylated, it's galactose because I've drawn C4 in. It's different from glucose. But I could, it's kind of immaterial for the discussion that we're currently having as a one-sided lecture. So turning that around, ether is good. Let's say we have a solvation shell around this. Ether is organizing itself around this thing the same way that any solvent organizes around any solute at any time. Cool. That's fine. That's not the answer. That's not what I'm looking for. There's something else ether can do to this oxalocarbenium thing to interact with it, besides just solvating around it?
Donating electrons to it?
Damn good guess, and I agree with you. So do you want to give me a bit more detail on what you mean by that?
Just the oxygen ether could donate its electrons to maybe the it should be the carbon, like the double bond carbon.
Okay. So do you want to rephrase donating its electrons? I agree with you. Can we just state that a little bit differently? Because donating electrons can mean, hey, take an electron. And then I become like, but is that what's happening? Or is the oxygen losing its electrons, or is it sharing its electrons?
Sharing.
Sharing, I like that more. And I agree with you. It is going to be to this carbon. And I'm going to draw this as an equilibrium because, like everything in this world, it's an equilibrium. Okay, I've drawn that beta. I could have drawn it alpha. It's gonna be one or the other. Right, and then this is an equilibrium. Together. So, the ether can come in, it can go beta, it can leave again, regenerate the oxalocarbenium. The ether can come in, go alpha, it can leave again, generate the oxalocarbenium, go in, become beta, equilibrium. There's an equilibrium set up between these three things. Of the two in red, which one is favored? I remember our discussion about the reverse anomeric effect.
So, but for reverse anomeric effect, it should be better.
Should be which
Not
one?
better, isn't it?
Beta. Yeah, so the
Yeah.
beta is preferred. And again, the reverse anomeric effect is not an anomeric effect. The anomeric effect is much stronger for the alpha. That CO bond is really, really weak. Its sigma star is really low lying. It's really accessible to the electrons. So the anomeric effect is very, very strong on the alpha here. The problem is it's positively charged. And so that positive charge needs to be stabilized by surrounding ether ion atoms, molecules, ethers molecules, by surrounding ether molecules. The problem is if it's alpha, it's sterically hindered by the rest of the ring. The other ether molecules can't gather around it properly to stabilize it. Whereas the beta is much more accessible. It's easy for the other ether molecules to gather around.
I also have a question.
Yeah.
I know this is not necessarily a attack, but well, usually when nickel uh, electron fires attack double bond, there's an angle. But does it
There's a
matter
Berge
here?
Dunitz angle, right?
Yeah.
What you're saying? Yep, and we have that here too. So we can do that. And you're absolutely right. There is still a Berge Dunitz angle. So let's take a look at that because what we're really and comes back to this. So if this wasn't clear, let's draw it in. Easier for other ether molecules to solubilize the charge, solubilize and stabilize the charge. So if we take a look at this, as I said, I'm drawing them as boats, but I said they're all half chairs. And so in this case, from this half chair, your nucleophile is going to attack the top because that's going to switch you towards a chair-like transition state. Whereas if the nucleophile attack the bottom, I'm getting to where you were going, Hazel, because I think it's a very interesting place you wanted to go. So that's high energy. So if you want to attack from the bottom, what you would need to do is you would need to flip your chair. So if want bottom, And we were just discussing why last class the bottom is preferred. And that's going to go through a chair-like. So I just did is flip half chair. Okay, but I haven't answered Hazel's question yet. I've just talked about drawing these as chairs and half chairs. So to answer Hazel's question, let's just redraw this for a second. Now we've seen how this goes. And what this is equivalent to is you have a pi bond, right? What the nucleophile attacks is the pi star, which is the antibonding orbital of that. And the antibonding orbital of a pi bond, I'm going to draw it over here. It should be here. I just don't have any space. Everything is identical in place, so I'm not moving any atoms. But I am going to change the bond angles a bit. So you have an antibonding orbital, and I did a pretty shitty job of drawing this, but I'll look this up. It's called the Bürgi-Dunitz angle. Dunitz actually died last week. And this is about 107 degrees. I have to look up the exact angle. It's escaping me right now, but it's over 90 degrees. The p orbitals in the bonding are basically lined up perfectly parallel, but in the antibonding orbital, they're pointing away from each other because they're repelling each other. So the electron density in the antibonding orbital would be repelled by the other p orbital, so they bend a little bit away from 90. And your nucleophile comes in at an angle. And it still does with these things. So with these oxalocarbeniums, they're still coming in at an angle. And the only thing is I'm drawing it as that boat because boats are easy to draw and half chairs are a little bit more confusing to draw. And we can think of it as a boat, and that's okay. But we have to remember that it's going through the half chair, and really the half chairs are interconverting and all of that stuff. But for the sake of simplicity, I'm not going to, we've already gone through that exercise. I'm not going to go through every time and flip the boat, go to the half chair, show the nucleophile coming in. I'm just going to draw it as a boat and say, okay, well, you know that what I'm really doing is attacking the half chair, and the half chairs are interconverting, and we're going to get the appropriate half chair to do the reaction. And your nucleophile is going to come in at the Bürgi-Dunitz angle. So this is an attack. There's nothing unusual about this ether attack. This is a typical addition of a nucleophile to a carbonyl equivalent. I don't know if that answers your question, Hazel.
Yeah, definitely. I just want to know if it's still there.
Sorry,
Thank you.
yes, I went into an awful lot of detail there. But I think it's valuable detail because I think for some people in the room that might be newer stuff. So if this is all really new to you, look up the Bürgi-Dunitz angle. Anyways, right, so reverse anomeric effect is basically in order here because we have a positively charged species right next to, positively charged atom right next to the anomeric center, and it's not well solubilized by the molecules because the other solvent molecules are big and bulky and they require space, and so they prefer to solubilize the beta. Okay. So with this setup, I don't know why I'm drawing in some lone pairs. Where do you think, what do you think is the most, so this one is, so we've agreed that C is better than A. So what about C versus B? Which of those two carbocations is more stable? Or anions is more stable? Cations is more stable. They're not carbocations. Which of those cations is more stable? I've only had one cup of coffee this morning. I obviously know a lot more. Saying I'm not sure is an okay answer. Because I think that's my answer. I can argue for both B and C on many cases. The thing is I don't think there's any way we can experimentally demonstrate it. My gut says C, but I'm not sure. But it's kind of irrelevant because if we're looking at these two and thinking of it that way, we're thinking of it wrong. Because we're trying to analyze stability of these in a vacuum, but they're not in a vacuum. They're drowning in freaking ether. There's ether everywhere. And so by Le Chatelier's principle, C is the resting state. Even if slightly less stable than B. Because Le Chatelier. Which basically says you push equilibria based on the concentrations of the reagents. And there's a metric ton of ether in there compared to everything else. And so the ether doesn't want to be a metric ton. It's going to go to the right-hand side of the equation. Okay. I also think the way I've drawn C, I'm kind of lying to you because I'm saying, hey, there's a bond. And there might not be. This is also an equilibrium. Not with that magically adding more carbons, but just sort of a dipole pair. I guess I should probably draw it as like that. And I'm putting a positive on the carbon because I could have put on the oxygen, it's a resonance structure, but I'm putting it on a carbon just to highlight the fact that that's where the interaction is. And so what that's doing effectively, and it doesn't really matter if you have a dipole pair or if you have an actual bond. Either way, you're blocking the beta face. The ether is sitting at the beta side. And even if it's not a full positive charge on the oxygen, because it's not a full donation of electrons, you're still having an interaction, which is increasing the positive charge on the oxygen, which requires solubilization by other solvent molecules. So you're no further ahead. It doesn't matter if you have a bond or not. It's easier to stabilize the charge when it's located beta than when it's located alpha because it's more accessible. Okay, so information. I now add methanol. Just small amount. So it's not solvent. What am I expecting this to do mechanistically?
Instead of ether?
Well, I've had the ether there, now I'm adding a tiny bit of methanol. So I've allowed this thing to form an ether. So mechanistic, and actually practically how you do this reaction is you take a sugar, you dissolve it in ether, you add your silver triflate at a cold temperature, you let it stir for about an hour, half an hour, 10 minutes, varies. Then you add a little bit of methanol.
I mean, the methoxy should come in instead of ether.
Okay, so where am I going to attack and what kind of mechanism am I going to use?
The same SN2. I mean,
SN2, exactly. Because we have an oxalocarbenium because we stripped away the leaving group, the bromine leaving group. The bromine carbon bond was a covalent bond. It was a weak covalent bond, but it was covalent. It sits there and does what covalent bonds do, which are sitting there. We've replaced that now with an oxalocarbenium, which is really unstable, and we've stabilized that by adding ether, which delocalizes the charge. Awesome, we like delocalizing charge. That is a good thing. The problem is it's more stable, but it's not stable. But now what we're doing is we're blocking the beta phase. And so I'm going to call it an SN2-like reaction. If methanol attacks here, doing that, this is an SN2. If methanol attacks here, this is actually an SN1 because there's no bond that's being broken. There's no leaving group. There's just an ion pair, but an ion pair is not a covalent bond. But it's an SN1 guided from bottom face only. So stereochemically, it's an SN2. So we can just call the whole thing SN2-like. It doesn't matter which of those are reacting, you get the same product. So we do know that the truth of the matter is kind of in between those two structures I drew there in equilibria. You have something that looks kind of like a very close pair, but not an actual covalent bond between ether and a sugar on average. Although I'm sure there are some covalent bonds in there sometimes when this gets displaced, and I'm sure there are some pairs. But we know it's not a full covalent bond because it's not, if it was a full covalent bond and it was SN2-like, you would never see any beta. You would only get alpha, but you do get some beta. So that tells you that the ether's coming in, going off, coming in, going off, coming in, going off, and occasionally it wanders away a little bit and you get a little bit of beta product. So this can be anywhere from 9:1 to 99.5 to 0.5 alpha to beta. I've seen worse sometimes, but not often. And there was a comment in the chat that came up, and I haven't checked the chat. Sorry, Michael, I missed your comment. You did purchase, thank you, but I missed what that was. I'll try and keep that up and available to myself. Good, okay, there, I got it all. So you get almost exclusively alpha this way. Why such a huge range? Well, it depends on the nucleophile, it depends on the sterics of the sugar, it depends on exactly which solvent you're using. It depends on the temperature. So that's why there's a range of these things, because everything depends on this. And even all the rules I'm showing you, I've actually done reactions in ether with glycosylations that should work, and I get mostly beta product, and I have no fucking clue why that works, because it's not supposed to. But again, but it's much better than if I didn't use ether. So obviously something's really happening that's really favoring beta in those conditions. Anyways, in general, this is a good enough rule for paper chemistry for this course, and it's a good thing to try. So that's, you get the same effect there with any solvent except acetylnitrile that reversibly interacts with a carbenium. And by what I mean is reversibly, it's non-protic, so that they can't lose a proton and make a permanent bond. They're like ether or THF or dioxane. They can make an interaction, but they can't break a bond to form the new bond to the anomeric center. So class 3, I said, was just acetylnitrile. So this is interesting. I'm fascinated by this. And I have a project going on in a group which is currently on hold to really tell if this is actually true or not, because there's no proof one way or the other. But the experimental evidence is you use acetylnitrile, you get the beta product, but exactly why is not known. But there is a good proposal. Okay, so I mix this with acetylnitrile. And acetylnitrile, you don't remember, is that. Okay. There's nothing magical going on here. Does the same thing as ether does. Nucleophilic attack from the electron-rich atom onto the oxalocarbenium. It's just acetylnitrile is special because it's shaped like a stick. What the hell do I mean by that? So remember the reason why we want to have charged things beta. And there's less sterics if you're beta. Okay, think about acetylnitrile. Is acetylnitrile more or less sterically demanding than ether? In both cases, we want to use these lone pairs to stabilize the growing charge.
I'm not sure what you mean by sort of demanding.
So does it take up more space? So if I'm trying to gather a acetylnitrile molecule, let's say I've drawn the structure there on the left. Okay? This guy here.
Yeah.
If I'm trying to gather ether molecules around it with the oxygen pointing towards the positively charged, most of that charge is actually going to be on the carbon. So if I'm trying to gather ether molecules around this, or if I'm trying to gather acetylnitrile molecules around that, can I get more ether molecules around it or more acetylnitrile molecules around it easily? Which one takes up less space?
Acetylnitrile.
Yeah, acetylnitrile is like my pen, right? Like here's the nitrogen, this nub part over here. Then it's got a straight triple bond carbon. So you know, I can stick a lot of pens directed at things. So all I need is this directed at stuff. Whereas ether is much more like my mouse. Like I need to sort of bring this whole thing in. And it's really bulky, and it's like that's my oxygen right in the middle there. It's bringing all this crap around on both sides. It's a lot bulkier to try and get this pointing towards things. So that's why solvents like ether really like the beta, because they're bulky. Acetonitrile though is really skinny. And so trying to get acetonitrile molecules around the charge isn't hard. And so what takes over is anomeric effect. Big positive alpha. We like that weak carbon nitrogen bond we've just generated. It's really stabilized by the anomeric effect. And so because acetonitrile is so small, you don't have this solvation effect that you get with all the etheric solvents, that they have to kind of bunch around it to stabilize, and so they have to go beta because there's more space beta. Here, space isn't an issue. Acetonitrile is tiny. So acetonitrile can easily stabilize another acetonitrile molecule. So, okay. But what I really love about acetonitrile is actually, it's not that, because what we could sort of, because the evidence is that the selectivity is amazing. It's if the selectivity was about the same for ether, we would say, okay, well, it's the same freaking mechanism you just did with ether, John. It's just you have acetonitrile alpha instead of beta, and then of course you're going to prefer the beta attack because the alpha side is blocked. It's not that simple. So what's proposed is, and there's some kinetic data supporting this, like sort of number of equivalents of solvent and rate order of reactions and that kind of thing, by mixing acetonitrile with dichloromethane. It seems to be dependent on having two acetonitrile molecules present. So what happens when you do that? Well, so I've got two acetonitrile molecules present. I'll do the middle one in a different color. So there's two acetonitriles there. Then if I bring in a nucleophile, do that in a different color. Of course, it attacks the positive charge. It's not a stupid nucleophile. And I like it because I like six-membered rings. So if I start drawing what this should do from this situation, loss of a proton, of course, just bye-bye hydrogen on the methanol. I can regenerate my acetonitrile and I deliver my nucleophile to a six-membered ring intermediate. This has been proposed by the guy who did a lot of this chemistry. His name's Richard Schmidt. He got this drawn out into an article. He's got absolutely no evidence for this six-membered ring intermediate. It's just so freaking elegant. I want it to be true. And we spent a couple of years in the group working away on trying to prove this, and I think it's not true. but I want it to be true. So I'm still teaching it because it's just too pretty. And it's deeply upsetting to me that I don't think this is actually how this goes now. But it might still go in some specific cases, and it's elegant. So acetonitrile prefers beta. And you can do that either because you got this fancy thing I've just drawn here, or you just have the exact analogy to the ether thing where, you know, acetonitrile blocks the alpha face, and so the beta face is open for attack. Do that SN2-like mechanism. So that's solvents. So we can tweak the conditions to favor the alpha or beta. So now actually we can see this. So if I actually take the example, because God knows the Koenigsegg has been studied to death. So you take more or less the same conditions, silver triflate, use diethyl ether, minus 40 degrees Celsius. And I think they used isopropanol as the nucleophile instead of methanol. You get a little bit of both alpha and beta. It's about 9-to-1 beta. Sorry. It's 9-to-1 alpha to beta when you use ether. Exactly the same thing. Only change I make is I switch to acetonitrile solvent. I always abbreviate ACN, but that is actually incorrect. It means nothing. Get 19-to-1 the other way. So you can really tweak the alpha beta ratio by just changing your solvent, which is pretty cool. These are ditto marks, right? Like same thing as above. This is one example where it works really, really well. It doesn't normally work as extremely well as this, where you get this like 3 orders of magnitude inversion going the other way. But it's nice when something matches theory. Okay, so the other parameter I want to talk about was temperature. So let's do exactly the same thing, except we'll just use glucose because it saves me a line. Treat this with, again, stick with silver triflate. We'll switch our solvent to dichloromethane. And you can sort of see why you wouldn't choose to use dichloromethane for these things, because you want either alpha or beta, so you would pick either acetonitrile or ether. Why pick something that's kind of wishy-washy and in the middle if you don't need to? The only reason you would do that is if you have solubility issues, because dichloromethane dissolves everything. Ether and acetonitrile aren't quite as generalizable for dissolving everything. Anyways, if I run this at minus 40 degrees, you know, for the sake of, I'll stick with isopropanol. Under these conditions, would I expect to see more alpha or more beta? Which one should I see more of? What should be the dominant product, alpha or beta? So we've talked about if you have anchiomeric assistance, you favor beta. If you have diethyl ether, you favor, or another participating solvent like that, you favor alpha. If you have acetonitrile, you favor beta. None of those things hold true here. We don't have any of those things. So what is just the inherent bias of any system? Does it prefer alpha or beta?
In this situation, the alpha is Measure product,
right? Why?
because, I mean, I just say because of the, because of the solvent and, I mean, regardless to the temperature or the other thing.
Yeah, well, it's a major problem because the anomeric effect is the only parameter that's really driving selectivity.
And the alpha is the kinetic product, so maybe because of the low temperature, it's the fastest one.
Alpha is gonna dominate if you're under kinetic conditions because you're gonna make it first. You're right. So alpha, beta, major, minor. Okay. Okay. And I liked everything you said there. So Ronaz, you get the follow-up question. What if I change my conditions a little bit?
But if we, with the help of antimeric effect, of course, beta will be.
Well, there's no
The most-
antiomeric, it's only anomeric.
Oh.
There's only benzyl groups here. There's no acetates or anything.
Yeah,
So yeah, anomeric effect, purely alpha. Well,
Yeah.
not purely, but majorly alpha, because again, we're stabilizing that half chair, we're stabilizing that addition because of the stereoelectronic effect of the donation of the electrons into this bond. So we're stabilizing the transition state that leads to that product. Now, silver triflate dichloromethane, minus 60 degrees Celsius.
oh.
Okay, so I've dropped the temperature 20 degrees. Now, I think this reaction would work, but you would need to be very patient. Very, very, very patient. So it's gonna be a lot slower. But
And
have I increased, so if I take whatever, let's say, I'm just gonna make a number up. I don't know what the number is, so I'm making a number up. Let's say this is 3-to-1. It's probably in that ballpark. I'm probably not off by more than a factor of 2. So if I drop temperature to 60 degrees,
maybe 3-to-2, for example.
you think it goes to 3-to-2 now?
Maybe, yeah.
Okay.
I mean, the difference I think become less.
Okay, if I drop the temperature, the difference becomes less. Let's think about that for a second. Here's your starting material. Here's your transition state beta. Goes to your beta product. And we argued that the alpha was the kinetic product, right?
Alpha, yes.
Okay, so here's your transition state alpha. Okay, so this is, this is a pretty standard reaction coordinate diagram. We have a starting material in the middle. We can go either left or right. We have a beta product. The beta is more thermodynamically stable because everything's equatorial, but it goes through a higher energy transition state to get there because the alpha transition state can take advantage of the anomeric effect even if it gives us a slightly less stable product. So we have this. This is the situation that we're almost always facing for every sugar, kind of these things. Okay, so let's say we have a temperature of minus 40 degrees.
Yeah.
I'm just going to draw a line. Because temperature is energy, right?
Yeah.
Okay. So
I think I said opposite.
and then let's say I have another temperature line of minus 60 degrees. And I'll change a color. I want to change a color.
Now I just said the alpha, I mean, will the number of the alpha product will decrease because it cannot happen really fast because the lower temperature will decrease the rate of the reaction. So which is why I said that the difference between alpha and beta product will decrease and regardless to anything else.
Okay.
Yeah.
let's take this apart because
Okay.
you're wrong.
Yeah. Yes.
Okay, so let's think about what's going on when we
Yeah.
lower the temperature. What
Yes.
what affects? Okay, so your logic is right. I think we're just somewhere you've gotten something backwards in your logic. So let's think about this for a moment. Because first of all, you're thinking about this right. You are thinking about this right. You're using all the right words. You're coming to the wrong conclusion. So something's going on. Okay. So on this, we agreed this reaction is under kinetic control, which means once the nucleophile comes in, it's more or less irreversible. You can't, once you make the product, game over. You're
Yeah.
not going back.
Yes.
Okay. So we're under
So-
kinetic control. So the product ratio is dependent only on the energy difference between the starting material and basically the peaks, like the size of the kinetic barriers. Right?
Yeah.
Okay. So, I need a slope and I need a pen. You can do this at home. Okay, I have a binder. I dropped something important out of my binder. This is my SOP binder for standard operating protocols in the group. Now it's got a little bit of trouble here. I'm going to try and rotate it like this. Okay, so you can see that I have a binder.
Yeah.
And we have barriers. So let's say basically what molecules are doing constantly is they're always going up and down these slopes. So here's like the starting material. It's at the very low energy. And here's, let's say up here, this big peak up here is our beta transition state. We need to get really high energy to get up to the top of this thing. Our alpha transition state is much lower in energy and much easier to access. So if you have lots of energy in your system, like you have a high temperature, I can be rolling my pen from, like my pen can roll up, because it's got lots of energy to roll up, and it rolls back down. That rolls up, it rolls down. It's got an average temperature. But that's going to be enough to get over this peak. Now, if I have less energy, I have less height to roll my pen. Now, the problem is this is really narrow. If I had a nice slope, it would sort of, roll back and forwards along the slope. But if I have less average energy, the pen doesn't move as far. So let's say I have lots of energy versus only a little bit of energy. If I only have a little bit of energy, am I more likely to get over the small peak than the large peak? Like if I have lots of energy, if my energy is way up here, like way above this big peak, I'm pretty much equally likely to go over either peak because I have more energy than either one.
Yeah.
Right? So
Yeah.
It's random chance which way I go first. If I have sort of intermediate level of energy like here, I have more than enough energy to get over this peak because I'm higher, but I don't have enough energy to go over this peak. So if I ever go this direction, I'm over. If I go this way, I'm not over. It's not enough energy. So I basically go really select over here. But now as I start decreasing this,
yeah.
I increase the chance, the ratio. If I have a little bit of energy here, I only need a little bit more random energy to get over this peak. I need a whole lot more random energy to get over this peak, and that's much more unlikely.
Yeah.
So as temperature decreases, you improve the selectivity for going over the lower peak. Always. Lower temperature reactions are always more selective.
Thank you.
But you're right. So I think where this happened was you're thinking, okay, well, and it's okay because I think because what we're doing is you're doing a different ratio thing. I think what might have been going through your head, you can correct me if I'm wrong, is you're thinking, okay, so at -40, I have a ratio of these two energies. And let's say that ratio is, let's say that's 1 and that's 3, just numbers. Then at -60, it's 2 and it's 4. And so that is a 1 to 3 ratio. That's a 1 to 2 ratio. So the ratio is smaller, so I'm going to favor the beta more because that ratio is smaller. I think that might have been the logic you were using. I don't know.
Yeah, yeah.
But the problem there is what we're doing there is you're trying to compare ratios, and what we need to do is compare absolute distances. Because if those are if that's a 1-to-3 ratio, it's not about ratios, it's about each extra kilojoule of energy needed is exponentially harder to get. So it's the first kilojoule is the same for both of those. The second kilojoule required, let's say it required 3 kilojoules. The second kilojoule required would be exponentially harder than the first one. And the third one's going to be exponentially harder than that. So 1 to 3, you only need to pick up 3 here. And 3 is difficult, but it's not impossible. Whereas here you only need to pick up 1. Of course, 1's easier. That's of course true. Here it's 2 to 4. That fourth one is so much harder than the third one. So it's much less likely, you're just so much less likely to be able to get 4 kilojoules of energy compared to 3 kilojoules of energy. It's just random chance if you can pick up that extra little bit of energy to get over that peak. So very few molecules are going to get over that peak because it gets exponentially harder the higher the peak gets. So it's not about the ratio difference between the two peaks. It's about the absolute distance between your lower point and the higher point. And as you drop your energy, you raise the overall absolute distance to the higher energy barrier and becomes increasingly more unlikely as you drop the energy. So lower temperature reactions are always more selective. And I can sit here and go through the math with equations and some differential expressions. I'm not going to because none of us need to do calculus. But if you want to, I can point you in direction some really good physical chemistry textbooks, which will basically take 20 hours to say the same thing. But this is a universal of all chemistry. It's just a truism of reactivity. The higher the energy barrier, it gets exponentially more difficult to transfer it. And so if you have 2 different energy barriers and you drop your temperature, you favor your lower kinetic product even more than you would otherwise. So kinetic product favorability increases as temperature drops. So what I would expect this to go under these conditions is more like 9 to 1. So going up from 3 to 1 to 9 to 1. So we get like 3 times more selective. It's probably actually greater than that, but again, pulling numbers out of my ass. Easy numbers to work with. So all this being said, all these effects we've seen so far are kinetic. The anchumeric effect is kinetic. The anomeric effect is kinetic. Because again, we're not stabilizing the product, we're stabilizing transition states and intermediates. The solvent effects we just saw, the ether and CO nitrile effect, those are kinetic. So if you can drop your temperature, you accentuate any of those effects. Temperature can never flip your stereochemistry. If you have a 2 to 1 preference for one over the other, changing the temperature can never make it 1 to 2 the other way. That's impossible. But it can bring it closer to 1 to 1 if you keep increasing the temperature, or it can increase it to 99 to 1 if you drop the temperature. The problem is, well, why wouldn't you always just drop the temperature really low and get high selectivity? Temperature control is difficult, and the lower the temperature, the longer the reaction takes. The longer the reaction takes, the more opportunity you have for side product formation, which will cut into your yield. So you'll start making something different than the alpha or beta, and the harder it is to maintain that. So it's always a trade-off between good enough selectivity, short enough reaction times, and low enough side reactions. Side reactions is normally because water got in somewhere and started destroying your molecule, because water always gets in and destroys everything. Cool. So in summary on this, solvents. Ether leads to alpha. CO nitrile leads to beta. Low temp accentuates all of this. And ammeric effect leads to alpha. Ankymeric goes to beta. Okay. So before we start covering a few things, I want to talk about the problem with manose. We need to talk about manose. So here's the problem with manose. So manose, again, we haven't drawn a lot of manoses. Manose has an axial C2. Okay, whatever. So if I do this reaction in, same thing we've just been doing, silver triflate, dichloromethane, minus 40 degrees, why the hell not? Nothing, and then methanol as a nucleophile. I'm gonna put methanol over the arrow because it's a nucleophile. No ankymeric effect, no solvent effects because it's dichloromethane, it's not one of the specialty solvents. So what you expect to see is the alpha product. Pure anomeric effect. Okay. I do the same thing in acetonitrile. Be really wonderful if it all worked great. But it doesn't. You still get mostly alpha in this case. And that's because although acetonitrile is coming on and off, this benzyl group, that whatever it is, actually doesn't matter if it's benzyl, it could be just methyl. It starts blocking that top face. And it makes it really hard to do this attack. It's like, okay, well, that's no problem. But if I use ether, isn't as bad as anything else though. All alpha. Because again, ether collects up at the top face, same kind of thing. All the attack comes in alpha. Okay. Ankymeric assistance helped me in the past to get beta. The problem is, of course, with manose, the ankymeric assistance comes from the top. So no matter what you do, you can't get the beta product. You know, with the other ones, at least you could rely, with every other sugar except manose and C2, similar kind of guys, talose, and there's some other ones whose names escape me because they don't matter. Everything you do leads to the alpha product. You can't get around it. So how do you get around it? Well, there are really a few good ways, not many. One is actually the one thing that we've seen already. It's one of the most reliable ways of doing it. Okay, we get that. And we treat that with silver metal. And so, as we said, we're not going to completely break the bromine carbon bond. We're just going to lengthen it. We'll get an SN2-like reaction. So with the SN2 selective promoters, we're going to kind of come across a few others. The only one we've covered so far is solid silver with bromine as a leaving group. You can get beta. I don't want to cover that. The other main way of doing that, I'm not going to talk about glycosylfluorides in this class. Is basically called the delivery assistance. And so what you do is you protect that sugar We'll talk about this a little bit when we get to protecting groups. Point of silicon assistance. Treat that with methanol. And then when I use my silver triflate and I add a little bit of, well, that works. You can add a little bit of F minus. You liberate that. And the way this works is, okay, we go through our oxalocarbenium. But of course, if you have a little bit of F minus or a little bit of acid, there's various ways of doing this. You can attack the silicon, and you can basically migrate that methoxy group over, because it's in close proximity, it's sitting directly over the oxalocarbenium. It's probably already partially forming that bond, and as soon as it can be liberated from the silicon by displacement with fluorine, it does. So we end up with is this. And another equivalent of F minus comes into the silicon and releases the C2OH. That's pretty difficult to do. we're gonna cover a couple more methods. No, you know what? Screw it. I'm just not gonna talk about it this year. I was normally gonna cover a few other ways of dealing with this, but I'm just gonna discuss with these two. We'll see one other example with trichloroacidimidase where we can get really good selectivity on manose. But I'll leave that for there. But these two kind of stand alone. One is because it ties in with the Koenigsegg that we've been talking about already. The second one is kind of a orphan approach. It doesn't really tie in with anything. But what we're doing here is we're doing intramolecular delivery. So if you're ever trying to do something complicated, intramolecular delivery can sometimes always be useful. We use it all the time to solve problems in chemistry because you're not trying to rely on intermolecular interactions. You're setting up the stereochemistry in advance and forcing into one option only. We're at 9:47. I think discussed manose, we discussed all the solvent effects today. You're good to go probably on all the assignments are posted. You're probably good to work through the first one. I am going to try and modify them if necessary, but I think all the questions on assignment one are fine. You can work through them. And so midterms based on the assignment questions. I would work through them. They take time. They are really freaking hard. And the other thing I'll do is if you email me, I might, how do I say this? If you email me, a copy of Demchenko's handbook might end up with you. It's a good textbook for the course. I have an e-version of the textbook. I don't believe the University of Windsor has a subscription to it, but I'm happy to share an e-version of the textbook with you. That could help if you want a textbook to go with this. Again, all the notes are online, complete set of notes from previous years. We have all of these. Please use any resource you like to work through ideally not another person, but you can work in groups to try and work through these assignments. If you have exactly the same answers on the exam, it's a little suspicious, but because you'll have a slightly different interpretation of it. But you can work with other people to work through the assignments, that's fine. My goal is you learn the material, not that you can remember all this stuff under an exam, so it's open book. You'll just need to be able to understand what you did, because I'm going to change the questions subtly for the exams from the assignments. And if you don't understand what you're working through, then you're in trouble. But if you do understand it's trivial, you'll be able to basically use the same answer. Okay, that's it. I'm done for today. I will see you guys on Wednesday. Please save everything. Keep.